set of people at the...
No, now there are not many. We are just 5 over here. They'll come. Because they want to go to the observatory, they'll come. Yeah. But numbers are small, that's true. And probably the timing. Okay. Fine. So hello everyone, and welcome to the last session, the last talk for our meeting. The offline participants still have the observatory trip, but this is the last session for the online ones. So welcome Professor Deshpande. Good to have you with us, and over to you.
Yeah, thanks, Priya. So we're going to pick the ball from where we left yesterday, which was basically I was introducing you first to some aspects of radio pulsars and how their emission is generated, and what are the unknown things and where we look for clues. And I had listed several things here. Any of you interested in details of this are encouraged to go to pioneering work of these people listed here. What we are going to talk more specifically today, but before I go further, let me look at the questions you might have based on the stuff that we visited yesterday. And I can see already one question in the chat box.
There's one, yeah.
Okay. So Saurabh Singh, all right. What is the relation between magnetic field and spin period of a pulsar? Yeah. So that's what, there is no relation between it. These two are independent attributes of the pulsar. One is tied up with the rotation, of course, which is, which is quantified in terms of spin period, and the existence of magnetic field, although tied in a very deep way to rotation, the exact value of it is not tied up with the period that you see at present. So the general distribution of pulsars is such that, let me go back to, this diagram is a good one, okay? So most of the pulsars sit in this island, what is called the normal pulsar island, on the left of this red line, in the range about 10 to the 11 to 10 to the 13 Gauss. As you can see that this is a log scale on the x-axis showing the period, and they will move in this diagram very quickly in this region, even if the rate of change of period is constant, which is not. But even if that were to be constant, you can imagine that this log step of 1 millisecond to 10 milliseconds or 10 milliseconds to 100 milliseconds will be crossed in a short time. And, the same time will be taken to cross similar amount in period change. And so you will find that it's like the traffic, when it slows down, you will find large number of cars. And so you will find that even if the so-called pulsar flow is uniform in the period domain, the way we have plotted, they will appear to cluster in this range because just the way the diagram is. On top of that, they also slow down their slowing down rate. Okay. So that's an additional complication. But so essentially, if you look at the pulsar distribution, let me see if I have any figure here which I can pull out. Probably don't have a ready figure. I'll bring it up later. You will see the pulsar island, which is a huge number of pulsars here, and then some of them here, which are these recycled millisecond pulsars, and there are some which are recycled through intermediate mass binaries. But the predominant population of pulsars is here, and there is no specific relation between the starting magnetic field and the period. After that, how things evolve, of course, depends on the way they lose energy and if any evolution happens for the magnetic field in the manner that is depicted here. But yes, there is effect on each other, particularly because in the interior, you have superfluid, superconducting matter, because of which the angular momentum is also existing in quantized form in terms of vortices, which are parallel to the rotation axis. There are fluxoids, which show the quantum magnetic moment, which are aligned with the magnetic axis. And these two are coexisting in a volume where naturally you can see two kinds of spaghettis getting intertwined. So when you pull one of them, which is what you need to do when you slow down the pulsar, or as the pulsar slows down, the vortices have to be reduced. As you do that, you also pull the fluxoids to regions where ohmic dissipation can be high. And so increase in the period can cause decrease in the magnetic field. Okay? But that's at a very slow level, and that's a subtle effect which has been used, in fact, invoked to explain how these different populations of recycled pulsars would appear. Otherwise, left on its own, the conductivity in the core is high enough that the magnetic field will not decay during the lifetimes of the pulsars. Does that largely answer your question? That was Saurabh, right? Okay. Any other question? People can just unmute themselves and ask the question instead of typing if that's convenient. So Sushant must have shown you elaborate introduction to pulsars where, she must have shown you the distribution of pulsars in the magnetic field period plane. Is that sounding familiar or not? If not, then I will pull out one of the figures to show you the distribution.
Yes, I think this B versus P was shown in all.
Correct. Yeah, and with lots of dots with different symbols and all that.
That's right.
Okay. Where in stellar cluster do NS mostly found? Okay, so the globular clusters are, are rich, hold large number of pulsars, particularly dense cores, where certain density is reached in globular clusters. You do see a significant population of pulsars, large fraction of them, of course, given the age of it, as well as the ages of millisecond pulsars also sort of in line with the kind of ages we talk of globular clusters. So they all long time has gone on since all this initial evolution has taken place. So you will find that there are a large number of recycled millisecond pulsars in the globular clusters. Many of them are in binaries, and those have actually been very attractive sets of pulsars to study lots of things about the cluster itself in terms of how the free electrons might be distributed within it and so on, which we can probe now by using pulsars as the probing tool, using dispersion measure. One can look for dispersion measure changes from one location to another location within the globular cluster. Yeah, so they are found in globular clusters. There are, in fact, clusters which have up to 30 millisecond pulsars. So they're pretty rich. Globular clusters, of course, have their own mind. They also, they are orbiting in their own ways, oscillating about the galactic plane and so on and so forth. Was that the sense of your question, or did I mistake it for something else? Yes. Okay. So maybe I can proceed with today's thing. Is that okay, Priya?
Yeah.
So I don't see any further questions, immediate questions.
Some questions. Okay.
All right. So the main emphasis of showing you the challenges that exist are relating to the radio emission of pulsars, which we really don't understand. We understand loosely that A, it has to be coherent. B, it has been seen to be highly significantly polarized in most cases, and that it comes from the magnetic pole region, because there is a very distinguishing signature of the pulsar position angle, the linear polarization's position angle changing in a very systematic way, which can readily relate to the dipolar field structure, as we would see if we're looking down the pole. And as I said, it's been used profitably to estimate several angles that are informative about the viewing geometry, as this is called, and we use them routinely to incorporate that information even in the population studies. But as I said, what leads to these multiple components, why one component is taller than the other, and so on, and why it switches between one signature to another signature, why the amount of polarization is the way it is seen, particularly the circular polarization is also seen to do something interesting. It changes systematically its position, sign, the handedness across the pulse. Sometimes it's correlated with the way the linear polarization changes, and so on and so forth. Sometimes it just has, it's single sign and doesn't change the sign through the pulse window. And that, again, people have been puzzled by such a thing. Whether we see the polarization that we see is a superposition of polarization associated with each one of the components, or is there some grand structure that is always frozen? These are the questions that are not understood fully. As I said, some of these things follow reasonable description and association or correspondence with the height and the frequency at which it prominently radiates. So to help these or to make progress, you need data, and thanks to Golden Line, they actually brought out a catalog of detailed polarimetric observations and multi-frequency observations on 300 radio pulsars, and these data are available publicly. They right now might appear not to be easily accessible in terms of the actual numbers describing the profiles and so on, but they are available individually. You can go to European Pulsar Network websites. You can download them. I think there is a facility to download the entire set as one piece as well. So this this is very rich data. It's something that has been available for last, you can see, several decades, and lots of work has been done using it. One of the things that remains to be understood is the link between, or the way the polarization fraction is shared between linear and circular polarization. But just looking at the pulsar profiles, just looking at the separation between, so what is understood is that probably we have a hollow cone, which, basically an annulus, which we cut and get, these two occasions on which we intercept the annulus and we see emission. And the size of the annulus is smaller at higher frequencies in terms of angle, and becomes broader and broader. It's something that we understood looking at this dipolar geometry. So we can ask from the center, what is the separation of this component, and how does it increase? If we account for the scaling, across frequency, will they all this put together? And is this structure relevant that we see from one pulsar relevant to the other pulsar, and so on and so forth? Okay. Of course, there will be modifications. The way these components will appear to be separated because of the viewing geometry, because of the inclination between the rotation axis and the magnetic axis, and so on and so forth, and where we intercept this annulus. So all this can be put together, and this was one of the sample exercises that can be done. And one actually used this, which is simply a distribution in the XY plane of the one quadrant of what I described as an annular beam, right? So if the annulus was that big, then the information really, given all the symmetries, can be viewed in form of one quadrant. And because there's no real distinguishing between top and bottom and left and right for this twofold symmetry. So when you do that, you find that the separations between different components, they all form a common structure, which is which you can study and model. And it was concluded that we require at least 3 distinct cones. So it's the conclusion was that we have a nested cone structure in pulsars where the emission can come from, and it might light or activate one of the rings based on. But there are examples where sometimes all the 3 rings are lit, and they are seen as distinct components. When you intercept this set of multiple rings, you will get different components. That's what is manifested here. This analysis needs to be looked at also from the way the polarization information is. We have used, of course, the polarization information here to infer the viewing geometry. As you will see, the information about the relative inclinations have come from polarization, but we have not used the details of the way polarization is seen to change across the pulse profile. Similar exercise done, we should also produce a map of polarization position angle orientation in this XY plane, and that's something that will be worth playing with, particularly given the certain jumps that you see. Whether these jumps are confined to any particular part of the annulus is not explored yet, because a collective picture from all these pulsar data has not been put together for polarization. you can see that when you look at the, so one of the other thing is, in general, the polarization is elliptical, and it can be always viewed as a combination of linear and circular polarizations, or superposition of two circulars with some phase shift, right, and relative amplitudes, or superposition of two linears with some relative amplitudes and relative phase shifts. You can make any number of combinations to represent the same observed entity. But if you were to stick to separation as linear and circular superposition, then, which is what is done routinely here, you will find you do not know the proportions of them. You do not know how each one dictates the other, and so on and so forth. So, as I said, that analysis is not yet fully done. There is no one single question one can ask in this particular case as yet. But even to distill out that question, one needs to have a close and hard stare at the data that we have in ways that will begin to bring out certain common thread. And that will require being at it patiently and looking at several aspects initially with a lot of patience and insight. So keen eye and asking the right questions. It's not the amount of data that is going to be the overwhelming thing. Is the lack of knowing what is the right question to ask to probe things further is the key. So people who have that patience and keenness to do that are most welcome to dive into it. But this is not something where something is done quickly, one knows the path, one simply pushes the numbers through something and then gets an answer which one can proudly go and mention to peers. So this could be a frustrating experience where no clue is forthcoming for a long time, and suddenly there might be some lucky breakthrough. But some systematic way of looking at this data to begin to look for common threads is essential, and that's something that is a motivation. So questions like, one can ask some specific questions. What decides the percentage polarization in the first place itself? So we know, because through observations we have seen how it depends on the frequency. The circular is sometimes, as I said, of one hand, sometimes changes handedness correlated with the linear polarization position angle. So I'm just reiterating what I just now said. Need to look at it carefully to see if and how the circular and linear polarization fractions are related in the first place. Are they? And why circular behaves in the way by changing handedness in a correlated way with linear polarization in some cases, whereas it remains of one sign in other cases. What are the differences? What changes between? Is there a separate population in terms of, or is it separable in terms of the way viewing is done, or is it some material outside the pulsar, in the circum sort of pulsar region, which is offering some propagation effect which increases or modifies the polarization. So there is, as I said, tons of data to probe this. I don't know how to get rid of this blockage that I'm having due to the Zoom thing. Normally it used to slide up, but okay. So you will see there are jumps, sudden jumps here. Okay. if you look at, there are very interesting things that occur. There are sudden polarization position angle jumps by 90 degrees. This track should have gone smoothly like that, but then piece of it is offset from it by 90 degrees. There are range of examples like that. In some cases, some of the jumps that you see are only relating to the fact that we are representing something modulo 180 degrees, and because it might exceed that range on one side, suddenly the next point is plotted starting from below. And so I think this has been largely taken care of in this figure, but so you will see a range of examples of the proportions of circular and linear polarizations, as well as of the position angle delts. So and the jumps have been understood by careful look at what happens by looking at each pulse polarization, each component polarization. The components are separated across the longitude, and pulse by pulse, you put a dot to see what the position angle was at any given longitude, and you get this sort of a distribution function or scatter diagram. And you will find that there are regions where both these modes coexist. Okay, of course, whichever dominates in terms of intensity will take up the final answer will be based on whichever of the two modes, orthogonal modes, is prominent, and that prominence can keep changing. And so, but what happens is as a net, whenever both these modes exist, the net amount of linear polarization decreases. So you will find that places where both these are prominently existing, the linear polarization is weak. Wherever only one of them begins to appear, the polarization percentage seems to increase. These are just the examples. People have studied these, and I think it's time to put together the clues that you have from range of observations done over decades, and trying to make sense out of it in terms of how there are, of course, pulsars where close to 100% polarization has been seen. So you're also reconcile with that situation, and what is so different there needs to be understood. Okay. So, so I think the overall sense of the project that some of you might feel interested in taking up is to really dig into the polarization aspect of the pulsars. There are, of course, other fun stuff you can do. It has been shown that there is microstructure in the pulses, in the sense, if you zoom in at high time resolution, you might see signatures of some diffraction pattern, like manifestation of the coherent radiation. And for different pulsars, such signatures have been seen, not in this the way it was seen for one of the pulsars. You see narrow pulses sometimes, and if you use the argument of light travel time, it will amount to a size of a bunch of charged particles of the order of the beach ball size. So, so you have several manifestations of the way the coherent emission is seen. There is no attempt to stitch across such signatures across the range of periods and magnetic field combinations that you have, and the viewing geometry. So we always see the radiation as it appears to us on time scales which are dictated not just by the time scale of emission, but also tied up with the rotation. You can have a slowly rotating pulsar which might make the, and a sort of frozen pattern of radiation, it will appear like, it's a long duration pulse. If the same pulsar with the same structure begins to rotate fast, it will translate to a shorter time scale. But intrinsically itself, there could be lifetime of that radiation where, even if you're looking at that pulsar all the time in the same orientation because it's slow rotation, you will find that some radiation lasts only for a short while. So it will just, come up and go. And so is not dictated by the rotation, but by the intrinsic duration of the emission. Where the duration is long and the rotation is playing the prominent role, you will see imprints of that. There are regimes where both of these are comparable effects, and then you will find an interesting combination of it. So again, going to microstructure, where one might see sort of the very intrinsic basic patterns and the timescales associated with it, they have not yet been fully related to either the rotation or to the intrinsic lifetimes of these emissions, or a combination of it. And that's something that you would like to do. Now, for any one of these things, unlike even the polarization thing, these data are not available as a coherent set anywhere. Okay, so you need to really go through the literature, compile the examples together, and begin to make sense. So as I said, there need to be such signatures exist in other pulsars and may have been reported from one, on occasional one occasion or other in different contexts, but they need to be put together. And so you need to pick up these clues that are spread over the literature during the past decades and put them together as a coherent set, possibly giving us information about, what dictates the kind of structure that we see and how it manifests in different pulsars. Okay, I will probably stop here and take any questions. So as I promised,
yeah, so thanks, Desh. So,
yeah, I'm purposely stopping here to see what, whatever I've said, there might be some questions, which I will not have time to answer because there's no further session. So
so there are some questions, right, in the chat window. Should I read it out or?
Right. Is there any evidence found about existence of pulsar in the center of globular cluster? As you can see, there are lots of pulsars, and they do go close to the center. Remember that this collection of stars, compact or otherwise, are in this region where they are orbiting in this potential provided by the collection of stars. And so there is, of course, higher density closer to the center, of higher mass density also. And so you will find that, each one of these objects is actually orbiting and in motion, essentially. So, of course, they would be visiting the central region as a part of their orbit. It's unlikely that there is an object sitting right at the center and stationary. So that's very unlikely. But yes, the pulsars are close to the center also. And so one can actually do the imaging. They can find out the, wherever it's possible, you can find out the distances based on the orbits that they might be having. Now, how do we know the orbits? we know that if they are in motion, apparent periods will change over time. The period derivatives will get modified. There is this Shklovsky effect that will change the rate of change of period apparent to us based on the motion of the object. So you can find out the radial motion, and from that you can infer because you know the gravitational potential, and you can see where such accelerations will be seen. Does that largely answer your question? Yes. In fact, there is, if you're interested in globular clusters details, you can actually look at, it's a very fascinating set of things. There are interesting binary pulsars there. You can even begin to conduct certain tests of, this can be done even for other binaries. You can test the equivalence principle in a very subtle way, where there are examples of highly circular orbit, in the sense very circular orbit. That means the ellipticity or eccentricity is very small. One can ask, how can such a thing happen while there is differential distortions of this modifications of this orbit can come from the gravitational potential, which is influencing its overall behavior, which means the two objects, unless they are influenced similarly by the rest of the gravitational potential, you will not maintain the circularity of the orbit. And so they're very interesting questions one can ask. You can follow the work of Paulo Freire. He has done a lot of interesting stuff on the globular cluster pulsars. He's at Max Planck Institute in Bonn. If you were to look for his name and his work. No, there's no name of the book. Paulo Freire, I can see if, let me see if I can. There was a great philosopher also, what is his name? Okay, this is the person I'm talking about. Can you see my screen? Hello?
Yes, sir. Yes.
Okay. So have a look at his homepage and see what the. So he's been looking at globular clusters pretty closely.
Okay. Something that is it is actually one article.
Pardon?
It is actually article, no?
No. There is a lot of work that he has done, and one of the things that he had advanced in early, he used to talk about it very enthusiastically then. I'm sure he does even today. Is the if you look at some of the work of his,
Okay.
you will find mention of pulsar mass measurements and test of orbital determination. Somewhere he would mention the test of checking the principle of equivalence. Okay.
Okay.
If that is what I was trying to mention. The highly circular orbit remaining circular, okay, is a puzzle, right? In the presence of, remember, the two bodies are made of, let's say, particularly if you have a neutron star and a white dwarf binary, then they are different material types, right? And you want to know whether the gravity works the same way on both, right? If it worked differently, then you would destroy or perturb the nice circularity if it began with that, right? Okay, where in stellar clusters do the globular clusters? So there is a question from S. Where in stellar clusters do? So yeah, so in globular clusters are rich communities in terms of, or they're richly populated with radio pulsars. And of course, neutron stars, which may not be working as pulsars because they are not pointing towards us. So they could be large number. As I said, one of the clusters has as many as 30 pulsars. We had even made a prediction about how many pulsars it would have. And we actually came to a number 30. And I don't think that number has been crossed. This was done by using the radio, the total radio emission that one has, and using information about the luminosity function of these pulsars in the radio. So you can see how much total light is coming, and you can see how the luminosities are distributed, and then make an estimate. Right.
Yeah, there's another one on chat. There you could see it. How
Yeah.
are pulsars formed? What's the mechanism? Like neutron stars and magnetars don't have that.
Oh, sorry, I had not. Okay. No, there are lots of questions below. I had not moved down the list.
Oh, yeah. Sorry.
No, that's okay. Is there any evidence found about existence of pulsar in the center of globular cluster? Is pulsar the candidate for object in the center of globular cluster? Is it? So what is the core consists of large number of objects, not just one star. They're pretty massive cores of the globular clusters. Can't be accounted for by just one star, but there will be all the stars rotating around. Okay, so how the jets of pulsars are formed and what is the mechanism? Like NS and magnetars don't have that. Okay, there are two kinds of context in which jets can be talked about in the case of pulsar. One is where there is a accretion. So there is a companion or material around the compact object, which is getting gravitationally attracted towards the pulsar once it crosses this bordering whatever the point where the pull from both of them is same, and then as after it falls on the surface, which might be channeled along the magnetic field lines and might get land up at the magnetic poles. The released energy can be seen in terms of both the X radiation that you get as well as the momentum that this material will have, and that will flow along the axis, a certain well-defined axis, and that will form the jet, or will be seen as jet. So that's one kind of jet. This is the basic mechanism there is not very different from other extragalactic systems that you see. Numbers and the scales are different, of course, but the essential aspects are pretty similar. Then you can have jets which might appear to be there in form of, so let me bring one example. Let me close this and go to folder Astro Sprint polarization. There. Stop. Okay. Close that. Exactly the wrong way. This is funny. All right. So I'm trying to get to the some place where I can show the strokes. All right. Okay, let me show you some pictures, which are, I'm just pulling out an old PPT. So there is another kind of so you see jets even in the X radiation around the you see jet-like features, okay, around in the nebulae, pulsar wind nebulae around pulsars. Okay, so that's, for example, this is a jet-like structure in the case of the Crab nebula, and the pulsar wind nebula is shown in this white and violet color. The red and so on is the optical radiation distribution. Does that answer the question about the jets? So these are particularly formed around young pulsars.
Sir, the jets are coming from inside, right?
No, there is, yeah, so there is a controversy about the jet, okay? We have a very different interpretation. We don't think for isolated pulsar. See, one is where you have accretion going on, correct? There the jets are pretty natural. Hello? Oh, somebody's talking in the background, I see. Okay, so there is generally so let me talk about the picture that people have. The prevailing wisdom, as we call it, okay, feels that the jet is a physical flow of matter along the rotation axis of the star, okay, in this particular case, pulsars that we're talking about with the pulsar wind. And we claim that there is no reason for any material to be flowing along the rotation axis, okay, for an isolated pulsar. All the action that we have is along the magnetic axis. And so our picture is very different. Our simple argument is the following. In the case like Vela or Crab pulsar, where these jets are seen, these are not accreting objects. They are not like the X-ray pulsars or black hole binaries or like AGNs. And so the jet along the rotation axis is very unlikely and also rather unphysical. And now we can ask where the action is happening. The action is happening along the magnetic axis. When would it appear? In what situation would it appear that something happening along the magnetic axis makes you feel that it's happening along the rotation axis? It would happen if you see the radiation only when the magnetic axis projection is along the rotation axis. When can that happen? This is what happens when we look at the pulsars. We get radiation from the magnetic pole, and when the magnetic pole is in the line projection along the projection of the rotation axis, then we see the radiation, correct? And so the only connection between the jet-like feature and the rotation axis must be that of projection. And this is what we say, and we actually invoke a simple jet-like radiation feature, which can come about even if particles are flowing along a pencil beam, so to say, in a narrow cone. You will find that they spread along what we can label as a fan beam, okay, with this kind of aspect ratio. Why does it happen? Because the particles which are moving outward are seeing toroidal magnetic field well outside the pulsar magnetosphere, or after the core rotation stops. The field is wound around the pulsar with symmetry or above the rotation axis. Now you have a cage with wires running in let's say these directions, perpendicular in planes perpendicular to the rotation axis, and you throw charged particles on it. You will find that the field will deflect due to the Lorentz force the motions. Otherwise, the motions would have been straight outward, radially outward, but they will also spread latitudinally. And this spread of charged particles will lead to radiation over a much extended range in latitude. And that is what, and when this points towards us, we'll see a flash of light, and the light is distributed in the latitudinal direction. And that's what we believe is this jet-like feature. There's nothing physical flow in terms of physical flow along the rotation axis. Although the radiation is seen only when this feature, oriented in different ways, becomes aligned with respect to the rotation axis that we see. Then that is when it's pointing towards us. So we see a jet-like flash and no physical physical motion of the material. And this picture fits in perfectly well to the extent that it can even explain various things relating to the features you see here. As you can see in this, this is the observation, and this is the model prediction. Okay, with the assumption that we see this flash of light due to radiation being seen only when that fan beam is pointing towards us. If you're interested, we can discuss more about it, or you can look at one of our papers on this subject. Okay, what details we seek from radio data to study pulsars? Yes, I think all the clues about what and how the radiation is produced in pulsars actually has come from radio. The radio discovery and the further studies have led to our understanding of how pulsars behave, both in terms of, so one of the key things is how they rotate. That information comes from just observing the pulses and their arrival times. It's such a straightforward measurement to do, is to have a clock and note down the times at which you see the pulses, and you will see that that changes as a function of time in manners that we study in area called timing of pulsars. And it gives you rich clues about what the pulsar is actually doing, what is it up to. So much so that people are thinking of using an ensemble of such objects which keep their time very well to see gravitational or detect gravitational waves. And they believe that gravitational waves passing close to these objects might distort the space-time locally, and that might change the time of arrival of pulses from that object in a manner which is frequency independent. Remember, there are effects about the arrival times of pulses which depend largely on the frequency, if those are associated with the refractive index being different for different frequencies during the propagation through the interstellar medium. So achromatic effects can be looked for, and that's what people are hoping to do, of course, which means that you're correct for everything else, and which is the biggest challenge, including the way we are rotating. Our rotation or our movement is dependent on knowing, or dependent on everything else in the solar system, how the solar system itself is moving with respect to the local standard of rest and all that. But even if we referred everything to the barycenter of the solar system, which is what people conveniently do, you will find that particularly that is adequate for the time scales over which we want to study this. You will find that even there are challenges. We actually have to know everything in the solar system to be able to define the barycenter. So yes, we can learn about the details of the way radio radiation is produced. We can learn about the kind of physical situations within the magnetosphere and what mechanism is at work in terms of what the electric field does. Electric field will certainly be generated because you have a rotating magnet, and how that is distributed, how that influences the action in the magnetosphere, how the radio radiation is produced, what gives the imprint of polarization, all that can be seen. We can also then see what these particles will do when they leave the pulsar. This is what they will produce. They will produce beautiful nebulae in the, around pulsars. And pulsars themselves sit in a cavity that they produce. So how the radiation interacts with the surrounding, how the radiation is produced in the first place. And we get to know basically all the secrets about the pulsars in terms of when the pulsar period is supposed to gradually increase with time, we see sometimes behavior like glitches, which probe. Let me go back to, if I have a transparency or two to show that. Let me see. I might have said something about the period. There are, let me move this window away. Okay, so here is a simple depiction of what we normally expect. If you can see this transparency, can you? Which says something about glitches. Is that visible?
Yes, sir, it is visible.
Okay, Yeah, so you will see time on the x-axis and period on the y-axis, and this is the gradual increase we expect for pulsars as a trend. But then suddenly at some time, you will see the period shortens, and then it continues on a track which is now offset. Sometimes it recovers this jump. So there are different cases. The amount of change, of course, is tiny. It's part in a million or part in a few tens of parts in a billion. What is happening is the exterior of the star, the crust, is slowing down in response to the loss of energy, which comes at the expense of the kinetic, rotational kinetic energy. Whereas the superfluid is not slowing down. And so there is this differential rotation between the exterior and the interior. Some stage, some threshold stresses are built up. They have to come to terms with each other, and what that amounts to is sharing of angular momentum or exchange of angular momentum between the core and the crust to bring them to rotate at the same rate. And that amounts to slowing down the core and speeding up the crust by a small amount. And you can see that such phenomena now begin to probe the interior of the neutron star, which we know nothing about or will never be able to conduct such an experiment simulating in lab a pulsar-like object with those kind of densities, because the stellar densities are extremely high in pulsars, which you must have learned about. So Sushant might have talked about glitches as well. So you can learn lots of things from the radio data based on what aspect you pick on, and it has its own golden nuggets that you can mine. Does that broadly answer your question? Because your question is, has a range of answers.
Yes, sir. Thank you so much.
So pulsar data on any time scale brings in information, rich information about different things happening in different aspects of pulsars. Although at the base of it, it's a very simple description we can make, that there are these, lighthouse-like objects which are rotating and giving us blips of light. They provide, they can also probe the intervening medium, and so much of information, rich information, has come about how the material is distributed, ionized material or magnetoionic material is distributed in our galaxy. Some of the best clues have come from pulsars. There they act simply as a shining source behind and seeing what the in-between material is doing. Any other question? I hope I have scrolled down enough to see. Last time what happened is I thought that was
Right.
questions and I had not
Covered what's in the chat, I think.
Okay. Yeah.
Any questions here? Yeah.
Okay. So I think I'm happy that I've managed not to delay you people
No,
for
no.
the trip. No, because it shouldn't happen because of a simply manageable thing.
Not at all. Not a problem. Pleasure. So,
Okay. So all the very best to people who are going to have exciting projects to do at the, as a follow-up of these sessions, I suppose. And if anybody wants to discuss anything, with me in the context of the stuff that I already mentioned, feel free to get in touch. But be aware that the aspects that I have mentioned are a long haul exercises. They're not some quick things that you can do, but the rewards also will be correspondingly rich in terms of the insight one would get into the subject.
Yeah, but I think your group has been working, right, for the past 2 years?
Yeah. So there are two sets of two projects already there. Okay. One of them is tied up with the distribution of pulsars in our galaxy and how that relates to the spiral arm structure. The second aspect I'm probing is the luminosities of pulsars, what they depend on, the radioluminosities. Are they relatable to any other observables in pulsars? I think Julie is working on that. Okay, very good.
Yeah.
So I think time to stop and let's see. First,
I will hear the applause from the offline people. That's all we can do. And thanks a lot. Thanks very much for being with us.
Oh, by the way, do you have so many people? I heard lots of. So there is a good offline crowd. I see.
I can turn.
You have a screen that you can turn to them.
One minute. Oh, okay. This is 1 minute. This is using the camera on the laptop. I'll just change.
I see.
This one, and this is the hall, and here you can see. You can see
okay.
Hands up, everyone. Yeah.
All right.
So obviously, since it was a Sunday, a lot of students.
Yeah. No. Sundays are tricky.
Yeah.
Even I had difficulty convincing myself that
Yeah.
I have to be up and running by the afternoon.
But the hall is not empty. The hall is not empty.
Yeah.
There are a few people here. Yeah.
Okay, great.
Okay.
Right.
Yeah. So see you.
Okay, thanks a lot, and have a nice weekend, whatever is left of it, and have a good trip to the observatory.
So thank you very much, and bye-bye. Yeah.
Okay, bye.
Bye.